Now beginning section 3.4, which begins on page 142, and this is methods of combining functions. So when we combine functions, guys, there are a number of different ways to combine functions. Let me start by giving you some generic functions, or some specific functions, I should say. F of x equals 2x plus 1, and let's do g of x equals x squared minus 3. We want to combine these functions together. Okay? Actually, let me change this up a little bit, guys. Let's make this x squared minus 4. And I'm going to make this x plus 2. I'm going to do it this way so we can actually see something else. All right. So what we're going to do here, guys, is we are going to take these two functions and we're going to combine them in various different ways. The first thing that we can do is we can add the two functions together. We can do f of x plus g of x. How do we do that? Well, we take our f of x, we're substituting, so we need to use parentheses, plus our g of x. So f of x is x plus 2. G of x is x squared minus 4. I distribute anything that needs to distribute. Clearly here there's nothing to distribute. So I just get x plus 2 plus x squared minus 4 is x squared plus x minus 2. That's it. You're just combining like terms. That's all you're doing. Distribute if you need to. Combine like terms. Where would you need to distribute? Maybe they asked you to do f of x plus 3 g of x's. So there'd be a 3 to distribute. That'd be the idea. Okay, now, one thing I want to mention to you guys is there's another way that we can write this. Instead of writing it as f of x plus g of x, there is another slightly different notation which says that we can also call this f plus g of x. These mean the same thing. There's no difference. It's just two different ways of writing the same thing, so don't let that confuse you. F of x plus g of x is the same thing as f plus g of x. It means you add the two functions together to get the combined function, and the variable you're using is x. All right, if we can add, what can we also do? Subtract. So we can subtract. So we can do f of x minus g of x, which is going to be f of x minus g of x. That's x plus 2. That's x squared minus 4. Here I have to distribute. I get x plus 2 minus x squared plus 4, which combines to give me negative x squared plus x plus 6. And how else do you think this could be written if we wanted to? F minus g of x. So again, just another way of writing the notation. It's a slightly different notation, but it means the same thing. So sometimes they'll use one, sometimes they'll use the other, just to make sure you're paying attention. Questions about those? Easy enough? Okay. You guys remember this from Algebra 2? It's not new. We did it all in Algebra 2. The next thing that we need to talk about is multiplication. And so now we can do multiplication, where we can do f of x times g of x. Now, very important, guys, notice I'm using the closed multiplication dot there. Why don't we want to use an x there? Yeah, it's confusing because x is our variable, right? We don't want to confuse it with another variable. So we're going to use the multiplication dot. Notice that multiplication dot is a filled-in dot. That's what multiplication is that symbol. I'll explain why that's important in a minute. So this is going to be f of x times g of x, which gives us x plus 2 times x squared minus 4. How do I work this out? FOIL. So this gives you x cubed minus 4x plus 2x squared minus 8. And if I write this in standard form, it's x cubed plus 2x squared minus 4x minus 8.
And you can always just go farther. Would that be like the ending?
That's all you'd have to do. Yeah, if you try and factor it, all it's going to do is get you right back to here, which doesn't do us any good. We started there, right? So you want to simplify it by multiplying it out. All right. We can also divide. F of x divided by g of x. Now, Before I do that, guys, what other notation do you think we can use for this?
F times G.
Yeah, you can either write it as f times g of x, or you can just write it as fg of x. Right? If I just glue the f and g next to each other, that means multiply, right? So there's a couple of different notations that all mean the same thing there. It means exactly what you think it means. There's no trick there. Okay, f divided by g of x is going to be f of x divided by g of x. Now, we have to simplify this. In order to simplify this, what am I going to have to do if I can? Factor it. The top does not factor. It's all one piece. The bottom factors into what, though? X minus 2, x plus 2. Again, guys, here's getting another chapter where we have to know factoring. So what could show up down there? Difference of cubes, sum of cubes, grouping, pseudo-quadratic. Any of that stuff can show up in this problem when we're dividing. So now what simplifies? Nope. 1 over x minus 2. The x minus 2 can't jump to the top, guys. When things cancel, they don't leave you, they don't disappear. They just become 1. So it's 1 over x minus 2. Questions about any of that? Now, will they always simplify? No. If nothing factors or nothing cancels, then it just stays the way it is. They won't always simplify here. Now, how do you think we can write this? Another way.
F over G of x.
Oh yeah, f over g of x, exactly. You'll see it like this. Now, typically they will write it like this. F over g of x, like that. Technically, I guess it could be written like this too, right? But I've yet to ever see it written that way. I don't think you see it in your book that way, if I recall. Okay, so you don't really have to worry about that. But obviously, if you saw that, would you know what they meant? Yeah. Okay. Now, I want to talk to you guys about something important. When we talk about domain on these problems, there's something very important to talk about. When we talk about domain, it is very important that you look at the original functions. You have to look at the final form of the function, and you have to look at every step in between. Should have been a space in there. You have to look at all three of these things when you're figuring out domain. So for example, if I have x plus 2 over x squared minus 4, right? What's the domain of this function? What is it? Just this function, the first piece, x plus 2.
Wait, what? Was it
What's the domain of this function? Looking at domain.
X is equal to negative 2.
No. All real numbers. Does it fit into either of our problem categories? Do we have x's in the denominator? Do we have x's inside of an even root? And it's all real numbers. What's the domain of this one? All real numbers. We don't have x's in the denominator. We don't have x's inside of an even root. So we multiply this all out, and it gives us an answer, whatever it was, x cubed plus 2x squared minus 4x minus 8, right? What's the domain of this thing? All real numbers. So what do you think the overall domain is? All real numbers. If you don't run into any problems anywhere along the way, it's all real numbers. Now notice, guys, we checked the originals. We checked the final answer. What didn't we do? We didn't check what happened when we put this together. Okay? When I put this together, does this whole thing as one piece fit into any of the problem categories? No, so it's also all real numbers. So this is correct. The domain is all real numbers. Now let me show you a different problem. What happens if I do this? What happens if I have my g of x is equal to x squared minus 4? And what happens if I have my f of x is equal to x plus 2? Okay, what's the domain of this one? All real numbers. What's the domain of this one? All real numbers. If I do g divided by f of x, that's going to be g of x divided by f of x. That factors into x plus 2, x minus 2. over x plus 2. Those cancel, leaving me what this time? What's the domain of this? Yeah, over 1, but it's just x minus 2. So this is different than the other division one I did. The other division one I did was f divided by g. This time I did g divided by f. What's the domain here? All numbers. So what's our final domain? Very good. This was all real numbers, this was all real numbers, this was all real numbers, but what didn't we look at? We didn't look at the stuff in between. What domain category problem do these fit into? X is in the denominator, so what do the x's in the denominator tell us? They tell us that x cannot be negative 2. Therefore, when I put all these together, this ends up being my domain condition. It doesn't matter that I could plug negative 2 into the originals. It doesn't matter that I could plug negative 2 into the final answer, guys. If I was plugging in a negative 2 for x and x, would I ever get from here all the way to there? No, because what would happen as soon as I hit that step? It'd be undefined. Why? Can't have 0 in the denominator. We wouldn't be able to get any further, guys. We would be dead in the water there, and we would never get this part. Does that make sense? So you have to look at all the in-between steps as well. Otherwise, you would never get from the start to the finish. The problem would fall apart in the middle somewhere. So we have to make sure we throw out any numbers that would cause us to not get from the beginning to the end. Does that make sense to everyone? Okay, so don't just look at the originals, don't just look at the final answer, look at every step along the way, and anything you have to throw out along the way, you have to throw out in the end. That's how domain works. All right, questions about that? Okay, the next thing we need to talk about is we need to talk about composite functions. Composite means a combination, a blending. So if I have f of x is equal to x plus 2, and I have g of x again is equal to x squared minus 4, we can see something that looks like this. The way that you read this thing is f of g of x. That's how you read that. Whoops. Now stop and think about this, guys. If I have f of 2, what does that mean? Plug 2 in for x, and you would get 2 plus 2, which is 4, right? What if they asked us to find f of a? What would that tell us to do? Plug a in for x in the f function, and you get a plus 2, right? What if we're asked for f of x plus h? Right. So this would be 2 plus 2. This would be a plus 2. This would be what? X plus h plus 2, right? And then you would continue to work these things out, right? So the question is, what does this mean, f of g of x? Exactly. It means take the f function,
Put it outside.
it means take the f function, which is x plus 2, in place of all the variables, you put a parentheses, and what goes into the parentheses? The g of x function, x squared minus 4. So what you're doing, guys, is, do you see it's the same notation as f of 2 and f of a and f of x plus h? So because it's the same notation, you have to use it the same way. It's just that instead of plugging a particular number in, we're plugging in a whole other function. Is that it really news to anybody? No. It's got to work the same way. It's only when you try and make it work differently that you get the wrong answer. When you overthink it, when you make it harder than it is, you get the wrong answer. If you don't overthink it, you're going to get the right answer. So this would now give you x squared minus 4 plus 2, which is x squared minus 2. That's the answer. What would g of f of x be? What would that tell us to do? Plug f into g. So I take my g function, okay, I replace my x with parentheses, and what goes into the parentheses? F of x, which is x plus 2. Now, what do I have to do to square this? Foil it. Very good. Don't make the algebra 1 mistake and just square each thing on the inside. That's x squared plus 4x plus 4 minus 4, which ends up giving us what? That's it, because these cancel. They won't always cancel, but they do on this one. Everybody see how that works? This is called compositing functions. This says f of g of x or g of f of x. Another way to say this is f composite g or g composite f. And there's another symbol for doing that. What's the symbol for composite? You guys don't remember? It's a little open multiplication dot. That's why I was stressing that the regular multiplication dot is a filled in dot. Because if you don't fill it in, it means something different. If you have a multiplication dot that is hollow, that doesn't mean multiplication, it means composite. It means you take the second one and you plug it into the first one. Everybody see how that works? So there's no difference between g of f of x and g composite f of x. The second one goes into the first one. Just a different way of writing it. Now, could you composite more than one function? More than two, excuse me.
No.
Sure. We could do f of g of f of x. What would this tell us to do? What would we do first?
We'll write the f of x as 1, put x plus 2.
Where do we start, the outside or the inside?
Outside?
Got to start on the inside, guys. You have to plug f into g, just like we did here, right here. And then you take that answer and plug it into f. You have to work from the inside. Right? So what we would do is we would take the g function, x squared minus 4, we would plug f into it. We would get this answer. Then we would take that and plug it into f. So we would take x plus 2 and plug this answer in here.
Wait, why x plus 2?
F of x is x plus 2. So this is x plus 2. And in place of the x, we're going to put this whole thing in. Exactly. Do you see how it works?
Yeah.
So do you see it's the same idea, guys? You're just applying it more than once. You plug f into g and get your answer, which gives you this. And then you take this and you plug it into the f function, because that's the one on the outside that you haven't used yet. So you work your way from the inside forward, just like with transformations, right? Start on the very inside, work your way forward to the left. Okay. Now, could you composite a function with itself? What would that look like? Well, it would look like this. It would look like f of x. What does that tell us to do? It tells us to take f of x and plug it into f. So we take x plus 2, and what do I plug into it? X plus 2, which gives us what? Could I do f of x? Yeah, that would tell me to take f of x and plug it into f, which would give me x plus 4. And so now you would have x plus 2, and into that you would plug your x plus 4, which would give you x plus 6.
You put x plus 2.
Sorry, thank you. There should have been a 4. I jumped ahead because I had the answer in my head. Thank you. Do you guys see how that works? Now, this is very important, guys. When you are compositing a function with itself over and over and over, what you're doing is you're plugging a number into the function and getting an answer. Then you're taking that answer and plugging it back into the same function to get a new answer. Then you're taking that answer and you're plugging it back into the same function to get a new answer. And you can do that over and over and over ad infinitum, right? You guys know what that means? Yeah, infinitely, right? Forever. Ad infinitum. You ever see that? What language is that?
I don't know.
Yeah, you do. Latin. It's Latin. Ad infinitum means to infinity, right? So you're going to keep repeating that forever and forever and forever. This concept, guys, compositing a function over and over with itself, is called iteration. And every time you plug it back into itself, that is another iterate. Okay? Now, we can do these things with all kinds of different things. We can do this with numbers. We can do it with functions. We can do this with pasta dough. Any of you guys ever watch TV Food Network? Never seen them use a pasta rolling machine where they take a wad of pasta dough and they put it in a machine and turn the crank and a flat sheet comes out? Then they turn the dial and they put it back into the same machine and turn the crank and a flatter sheet comes out, a thinner sheet, and they do it till they get the thickness they want. Okay, that's the idea of iteration, plugging back into the same machine over and over and over. Okay? You can also see these in this room, guys. The fractals in the back of the room, those are nothing more than graphs of iterates, of what we call recursive functions. When you composite a function with itself over and over, every time you get an answer, you plug it back in, get a new answer, plug it back in, get a new answer. That's called a recursive function. It's referencing itself. When you plug in these functions, these recursive functions, and you test all the points on the graph, and then you decide what color to make it based on the behavior of that particular point, and then you go and test another point, when those points are involving imaginary numbers, complex numbers, a plus bi. Okay, these are not xy graphs, guys. These are a plus bi graphs. So if you want to see what imaginary numbers can look like, look at those pictures. There are imaginary numbers going on in those pictures. And every pixel is tested to see how it behaves, and then based on how it behaves in this recursion, whether it gets bigger and bigger and bigger, or whether it gets smaller and smaller and smaller, and how fast it gets bigger or smaller, or goes to 0, then they determine what that pixel should be colored. Should it be light blue? Should it be dark blue? Should it be green? Should it be red? Should it be white? And when you put all those pixels together on a computer screen, those are the graphs that you get. So every one of those colored dots means something. Tells us something about that number when it's iterated over and over. All right, guys, questions about any of that? Okay, the homework assignment. You're not going to be tested on that, but it makes it visual so that you can see that this stuff really does exist. It's tangible. You guys are going to do 3 through 33 trips. I'm going to resist the temptation to say something. She wasn't even listening to me. I said I was going to resist the temptation of saying something, and you didn't even listen to me. All right, guys.